One LLM answer is a coin flip. Let's make a better process. After this, you'll understand how to assemble a pipeline that samples answers, votes on them, and filters low-confidence choices. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Start with the problem. Large language models can give one good answer or one plausible-sounding error. If you rely on a single greedy response, you can miss the right solution. Self-consistency reduces that risk by drawing several samples and asking which answer the model agrees on most. Teams use this when accuracy matters more than the absolute lowest latency, like for automated grading, code generation checks, or question answering where mistakes are costly. Intuitively, think of polling witnesses. Each sample is a witness report. If many reports match, you trust the consensus. If reports scatter, you might abstain or ask for more evidence. Strengths are improved reliability and simple interpretability. Weaknesses are extra calls and the need to normalize answers, so different formatting does not hide agreement. We will build a clear, minimal pipeline. It samples multiple answers from a model, normalizes surface differences, votes to pick a consensus, rejects weak majorities, and compares that result against single answer baselines on small labeled cases. The goal is a reproducible experiment you can extend to larger datasets later. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a simple voting baseline that preserves every sample and then picks the most common reply. This snippet turns several sampled LLM answers into a simple majority vote. A single call can land on a weak answer. So the first move is to preserve multiple answers in samples, instead of overwriting them. Counter records how often each answer appears, and most common one picks the answer with the largest count. The share variable converts that count into a fraction, which is easier to compare across runs with different sample counts. The visible output shows the winning answer and its vote share, giving you a first reliability signal instead of just one raw response. That initial vote works, but formatting noise often breaks agreement. Next, we add a tiny normalizer to collapse surface differences so the vote measures real agreement. This example fixes a common failure mode where equivalent answers look different as strings. If the model returns capitalization, spaces, or trailing punctuation inconsistently, a raw majority vote can undercount the real agreement. The clean function applies a small, explicit normalization rule. Then choices becomes the vote list that counter sees. This is intentionally narrow. It handles surface formatting, not semantic equivalence between different phrasings. The visible output shows one normalized answer with 3 normalized votes, so the vote reflects answer agreement rather than formatting noise. Now we should check whether voting actually helps in practice. We add a tiny evaluation harness that compares single answer accuracy to vote-based accuracy on labeled examples. This code checks whether voting actually improves the result on labeled examples. The cases list keeps a prompt label, a gold answer, and multiple sampled answers together, which mirrors the shape of a small experiment table. Single hits scores the first answer only, while vote hits scores the majority answer from the same samples. That comparison matters because self-consistency adds cost. So you want a measurable lift rather than a nicer-looking process. The visible output shows accuracy change across evaluated cases, making the benefit observable before you scale the experiment. Voting can still be misleading when the vote is split. Next, we add a confidence gate so the system can abstain when the top answer lacks sufficient support. This snippet adds a guardrail for cases where the vote is too split to trust. A majority answer is useful, but a one-vote edge across several samples can still be shaky, especially when you are comparing prompt variants. Min-share sets the minimum fraction required before decisions keep the answer. Otherwise, the result becomes abstain. Raising min-share makes the system more selective and may reduce random wrong answers, but it can also leave more questions unanswered. Lowering it increases coverage, with less evidence behind each accepted answer. The visible output shows how many answers passed the gate and how many were abstained. Finally, we wrap these pieces into a compact experiment runner so you can compare decoding policies and log outcome metrics. This example turns the pieces into a minimal experiment loop you can compare. Configs represents 2 decoding policies, 1 answer with full confidence, or 3 samples with a vote share threshold. For each configuration, the code reuses cases, scores only answers that pass the gate, and appends a compact run record containing accuracy, coverage, sample count, and threshold. In a real experiment, runs is the kind of structure you would log to your tracker, with prompt version and model settings. The visible output shows the selected baseline's best accuracy and answered count, balancing correctness with how often the system responds. Mapping this toy loop to a real project is straightforward. Replace the small cases list with a dev split from NaturalQuestions or a custom QA set. Keep the same flow. Sample, normalize, vote, gate, and log. The run records translate directly into dashboard charts for accuracy and coverage. What it is: a sampling plus voting pipeline that turns multiple model samples into a consensus answer and a vote share signal. When to use it: when accuracy and explainability matter more than the lowest possible latency. For tasks like grading, QA, or code synthesis checks. One caveat: it costs more model calls and needs normalization rules to avoid undercounting agreement. Tune the sample count and the min-share threshold next. For example, try increasing samples from 3 to 5 and sweep min-share to see how accuracy and coverage move on your dev set. That change usually gives the clearest improvement for this exact pipeline. If practical AI engineering helps, subscribe and watch the AI engineering videos.